call visible light. And that's what I'm showing. It's missing something there, but you can see between 400 to 500, what is that big color? 400 to 500 in that picture. 400 to 500. Blue. So between 400 and 500, it's called blue. 500 to 600, what is the color? Big general color. Greenish yellow, right? Green. Green band is between 500 and 600. And between 600 and 700? So red. So three major bands. Blue, green, red. These are the three major wave bands plants absorb in photosynthesis. I will say this. Although we call between 400 and 700 as the photosynthetically active radiation, is a little bit on both ends plants absorb. So let's say plants also, we have research showing that plants can absorb light at 385 nanometers. 400 is, I said 400 is cut off, but I'm now saying that a little bit, 385 nanometers, which is UV, ultraviolet A radiation, UVA radiation. Plants do take that, a little bit of that. Plants also take a little bit beyond 700, up to 750. It's called far red. Okay? Fringes. So photosynthetically active radiation is 400 to 700 nanometers, but plants do absorb a little bit on both ends, a little bit of UVA and a little bit of far red. The reason why they are not that important is if you just give them that light, the efficiency is so low, they won't grow well. They do absorb, but they don't grow well. So for the rest of the discussion, we're going to use 400 to 700 as our band, okay? The big wave band where photosynthesis happens. All right? That's called PAR, photosynthetically active radiation. All right? This is, I'm going to talk a little bit of physics of light, not much, a little bit. This is basically the classical work of Max Planck and Albert Einstein. Basically what we know is light exists as both a wave and a particle. You will not see the particle nature of the light unless that wave hits something. All right? So light is traveling as a wave. You won't see that photon particle. But when that wave hits something, then you will notice that, oh, there is a photon there. It's confusing, but that whatever Einstein did, a lot of things are still confusing to many scientists. But it's a great research. He got a Nobel Prize for the photoelectric effect. He discovered that it's a particle, right? But light exists as both a wave and a particle. And the reason why I want to say that it has a wave nature and a particle nature, because we are now going to derive two terms related, one to wave nature and the other to particle nature. Okay? Let's start with the wave nature. Very simple. You know waves, right? Water waves. You throw something in water, the waves are created, and as the waves are moving away, their energy gets dissipated. So the way you know that there's a wave moving is by looking at its energy. The energy is flowing, right? So with wave nature, we can determine the energy of light. With the wave nature, you can determine the energy of light, what we call irradiance. Okay? How much energy is this light carrying? That energy is what is used in photosynthesis, right? Very, what's your name? Uday. Udit. I'm just going to, whoever answers the question, I'm going to try and remember their names, okay? It's the fastest way to remember. But you get irradiance, that energy measurement from that measure. So how do you get that? Look at that. There are two types of light waves. One is a red light, right? And there's a blue light. Just a cartoon, just an example. Okay? And the wave has wavelength, right? Every wave has a wavelength. Here's the distance between, you see there, the two top ends across there. Okay? That's what is called a wave. Okay? In this particular picture, those arrows are kind of moved. I don't know why, but just look at that red wave, and you see there are two peaks. The distance between those two peaks is called the wavelength. Okay, and in this case, the wavelength, for example, is, let's say, 660 nanometers. You know the red band. The red band is between what? 600 and 700, right? Here, let's say this is 660 nanometers within that band. Okay, that 660 nanometers is the distance between those two peaks out there. Okay? That's why it's called 660 nanometers. Once you know that wavelength, you can measure the energy of that light using an equation. Hc by lambda, very simple equation. You may have heard about this in your probably earlier classes. Hc by lambda, Max Planck's constant. This is the classic work of Max Planck. Okay? So basically what? H is the Planck's constant and you got a value there. C is the velocity of light and lambda is the wavelength. What is the wavelength in this case? 660. You plug in those numbers and you get the energy of that photon. You can do the same thing for blue, 400 nanometers. Change it and you get that number. Now here is the question. We'll see who will answer first. Which, blue or red, which one has more energy?
Blue.
Why?
So
And why is red? You said red, right? We'll get to you. But
because it has shorter wavelength and here wavelength is in the denominator, so when we divide with the shorter number, we
You
get
get
a greater value.
did everybody understand that? Did everybody understand that? You're going to do some math this afternoon. So the color of the light is important. The blue has more energy, red has less energy, right? Compared to blue, simply because it's got a different wavelength. So here we are actually able to get the information about the energy that light is carrying from its wave nature, from its wavelength. That's why that wave nature is important. Now, one more extra, we'll go a little bit deeper. All right, so blue has more energy. We all agree. Based on Max Planck, yeah, we got it. But I'm going to give, let's say, plants all the time blue light. Because I'm thinking, oh, I'm going to give them a lot of energy, so they're going to grow well, big. What happens if you give plants a lot of energy? You can damage plants. You'll actually see when you give plants a lot of blue light, they become smaller. The reason is this. Plants have adapted themselves so that they can use the energy of the red light to the maximum efficiency. Meaning, whatever that energy that 650 nanometers is carrying, that is enough to activate photosynthesis. That is enough to excite the electron. You know that electron transport chain that you will learn in photosynthesis? That is enough to excite the electron to the next level. If you give more blue light, you are exciting the electron but really higher than needed. And that excess energy is just a waste. For some time, first 1 week or 2 weeks, you keep on giving more blue light. Plants try to release that excess energy as heat, but afterwards, wow, there's too much stress. They're going to become smaller. So, this is an important thing to remember. With LED lights, you can customize how much of the blue you can give, how much the red you can give, and how much of the green you can give. And now I'm telling you that don't give too much of blue. Sunlight has got almost 23% of blue light. You can come up with an artificial light where you can reduce the blue light to only 10% and give a lot of what color? What color is, did I tell you that has this right amount of energy?
Red.
Red. So if you give a lot of red color, the red color is sufficient to drive photosynthesis. It's got the right amount of energy. The plants won't get stressed. So give 85% of red light and 15% of blue light, enough to grow healthy plants. All of these applications go back to that wave nature, the energy piece. Okay? I want you to remember that. The wave nature will tell us about the energy that the light is carrying, and it is determined by the color of the light. Okay? Any question on that energy piece? Irradiance or energy. Okay? Does it make sense? Do you need something from us? I'm sorry. Do you need us to break something? Are we good?
No, sir.
We're okay? Okay. I'm kind of getting digressed. But in any case, so very important. So light travels as both wave and particle. The wave nature is useful because of the equation. It tells us how much of the energy the light is carrying. So now you can take light and you can, if you know how much of the blue, how much of the red, how much of green is there in that, you can calculate the total amount of energy. And if it's too much of blue and green, you can say, oh, this is not good light for plants. Let's give more red light. See, this is where that artificial lighting can become so important. Okay? Let's talk about that photon piece, the next one. So when we talk about particles of light, now we are talking about photons. Okay? Light particles are called photons. Photons. So I said the light travels as a wave, but when it hits something like a leaf surface or something, then you will see that it's actually one particle, one single photon hitting the plant, right? So here is a picture of sun, and from sun you are getting all kinds of photons, but I'm only focused on the visible band, power band, okay? And you have red, green, and blue photons falling, okay? We use a term called light intensity. So irradiance is what I described for energy. Here I'm talking about intensity, irradiance and intensity, okay? Irradiance gives you how much energy is there in light. Intensity will give you how many photons are falling. Number. No energy piece here. Nothing like that. It's just the number of photons falling in 1 meter square area in 1 second. Okay, let's go back. So let's say you put some light here. Photons are coming, right? They're coming as waves and they're hitting. Each wave is basically a photon. It's going down and hitting a surface. When you talk about intensity, you are not talking about energy at all. You are talking about number of photons coming from that source. Number. In 1 meter square area, how many photons are coming and falling in 1 second? Number of photons falling in 1 meter square area in 1 second. That's intensity. Okay, I want you to think about irradiance and intensity. Two different things. Irradiance is about energy, intensity is about number of photons. Two different things. Okay, and they come from the wave and particle nature. Number of particles of light falling in 1 meter square in 1 second is intensity. The energy that is being carried in a meter square area is intensity. Irradiance. Two different things. I want you to understand, if somebody says intensity, what are they really talking about? They are talking about number of photons falling in 1 meter square area per second. So let's say I take a light meter, a light sensor, and I put it right below this light. Okay? And I might see, for example, I'll just tell from my experience, 30 micromoles, and we'll get to this immediately. Give me a second. 30 micromoles per meter square per second. Okay? That's the number I would get. If I put a light sensor here, I get 30 micromoles per meter square per second. You understand meter square and you understand second. That's what I told you. Number of photons falling in 1 meter square in 1 second. Now where is this micromoles coming from? Who knows Avogadro number? Who knows Avogadro number? So what is that? 6.02 times 10 to the power of 23 of what?
Number of particles in 1 mole.
Any number of anything, right? Number of anything. So that's called a mole. It's called a mole. This is what Avogadro has come up with. 1 mole is equals to 6.02 times 10 to the power of 23 particles. Oh, okay. We are now talking about light particles falling in 1 meter square. Why not use the mole term? Because when you start counting, there are billions and billions of particles falling, and I can't simply say 3.5 billion particles per meter square. It doesn't make any sense. So we are now going to use the units for mole. So we're borrowing units from chemistry. Okay? But now we're not using mole. What are we using? We're using a micromole. What is a micromole then?
10 power minus 6.
A millionth or whatever. What is a million? Million is 1 followed by 6 zeros. So the mole divided by 1 followed by 6 zeros is a micromole. 10 to the power of minus 6, like you said, right? So that is a micromole. So now let's relate to the unit I just gave you. Micromoles per meter square per second. So if I tell you that, if I put a sensor here and it's giving me 30 micromoles per meter square per second, what am I talking here? 30 times 6.02 times 10 to the power of what? Micromole. 10 to the power of what? 17. Do you understand what I'm saying? If you don't understand, stop me here. Do you understand what I'm saying? No, I don't think you understand. It's okay, you can ask me. You can tell, I don't understand anything you're saying. It doesn't make any sense to me. It doesn't matter. You can ask me. Let's do the math. I wish I had a board to show you. But what I want you to remember is this. There is a term called mole in chemistry. Somebody came up with that. Mole. M-O-L-E. All right? This guy's name is Avogadro. And he said, what is a mole? He said, mole is something very general thing. It can be of anything. But a mole will contain always 6.02 times 10 to the power of 23 particles of that substance. It can be water molecules, it can be ice, it can be anything. A mole means 6.02 times 10 to the power of 23. What is 10 to the power of 23? 10 to the power of 23 means 1 followed by 23 zeros is a huge number. I don't know what you call it with. 1 followed by 23 zeros. That multiplied by 6.02. That is what he called mole. So basically what he's doing is, to put an analogy, simple analogy, I'll give you, let's say, a pile of paise, one paise. I don't think it exists anymore in India, but let's say I give you a big pile of paises, and I ask you to count them. Okay, you keep counting 1, 2, 3, 4. Rather than saying I have 2 crore paises with me, I'm asking you to convert into rupees. That's all. Rather than paise, tell me in rupees. Then you will say, okay, divide by 100, so I get it, right? It makes sense. Making a bigger one into a smaller one. That's what Avogadro did. Because everything he was dealing with in chemistry had lots and lots of big numbers, and he doesn't want to worry about those big numbers. He said, let's come up with a standard number, 6.02 times 10 to the power of 20, and call it a mole. Be done. So afterwards, everybody say, okay, rather than, these big numbers, I would say 10 moles, 15 moles. It used to make sense to people. 10 and 15 are easy to remember. So people used to convert into moles. It's very simple, making a big number into a smaller number. That's what Avogadro did. Okay? We are using the same thing with the light. Why? Because if I start counting those photons, they're like electrons. Tiny, tiny, microscopic things. Millions and millions and millions are falling on every second. It's impossible to give that number, big number. Why not use a mole and make it a smaller number? That's all it is. Very simple. Make sense? Does it make sense? That's what it is. But instead of moles, we're using micromoles. That's all. It's like instead of kilograms, we're using grams, or micrograms, or milligrams. We're using, instead of moles, we're using micromoles, a smaller number. All light measurements, intensity, come in that unit. Micromoles per meter square per second. Micromoles of photons falling in 1 meter square area in 1 second. That's the intensity. So if you go outside, sunny day, bright light, okay, you take a light sensor and you measure it. You know what the intensity will be? Approximately, you can get up to 1700 micromoles of photons coming down in 1 meter square area in 1 second. That is the amount of intensity of sunlight in that visible band, in that power band. Okay? But here I said 30 micromoles. Sunlight is 1700, this is 30. You see the difference? How bright sunlight is? 30 versus 1700. All of them in micromoles. But that micromole concept. You see that sunlight in a meter square area there, right? 1 meter by 1 meter. And if I count all those colored red, blue, green photons falling in that 1 meter square area in 1 second, think of raindrops. So let's say you have a big plate, okay? 1 meter by 1 meter plate. You put the plate outside when the rain is falling. Let's say you place the tray outside for 1 second and bring it inside, and then you measure the water. It's very, very similar. Or instead of raindrops, I'm talking about photons. Simple analogy, okay? That's what intensity is. But energy is different. Energy, you take the wavelength of the light, and then you use hc by lambda formula, and then you come up with a certain number of electron volts or joules of energy. Energy is something you get from wave nature. Intensity is what you get from particle nature. Two different concepts. But the most popular one is this, intensity, not energy. When we talk about plants, This is not correct, but this is what we all do. When we talk about plants, we always talk about intensity. We want to measure the light intensity. Okay? We don't really focus on energy. We consider all those photons similar, although they are not. Blue is having more energy than red. We consider all of them similar when we talk about intensity. We just measure the number. See, plants are very smart, right? They are actually able to sense the number of photons falling on them. The number of photons falling on them. That's what we are measuring with the sensor. Remember, the intensity is number, the radiance is energy. Two different concepts, and they stem back to the concepts of wave nature and particle nature of light. That's what I wanted to talk about on this slide. Okay? When it gets close to 1 o'clock, can one of you remind me, please? Because I forgot my power adapter, and this watch is dead. So I need to wait for 2 days to get the adapter. So I don't have, unless I have used my phone. But if it is 1 o'clock, please remind me. 10 more minutes? Oh, it was right there. Oh, wonderful. We've got 7 minutes. I'll try to get as close as possible. Okay? Now, there's another concept, and this is the most important thing I want you to remember. DLI. Daily Light Integral. Anybody works in greenhouse, has a greenhouse company? Anyone? No? Anyone heard about Daily Light Integral? Now, is this being recorded? Okay. I will not say that. But I will say this. It's a very simple mathematical concept. Okay? Take the intensity. I'm going to start with 100 micromoles per meter square per second. So when I say micromoles per meter square per second, I'm talking about intensity, right? So I'm giving you a number 100. Okay? What does this mean? This means 100 micromoles of photons are falling in 1 meter square area in 1 second. Now I'm going to ask you, the same amount is falling, but not in 1 second, but I want you to count for the entire day. Alright, not 1 second. See, I put a light, artificial light on plants. Okay, this light is giving 100 micromoles per meter square per second. But it's just 1 second. I don't want 1 second. I want to know the total amount of light the plants are receiving in 1 day. How do you calculate that? So you start with what? How many seconds are there in 1 minute? 60. How many minutes are there in 1 hour? 60. So 60 times 60, 3,600. So you take 100 micromoles and multiply. Can one of you please do the math for me? 100, all of you do the math for me. 100 micromoles times 3,600. How did I get 3,600? There are 60 seconds in a minute and 60 minutes in an hour. So if you do that math, you get the number of photons in 1 hour. Isn't it? Does it make sense? So 100 micromoles are falling in 1 second. Now how many photons are there in 1 hour?
3,03,000.
You got a number, right? Hold on to that one. Now let's say I'm going to turn the lights on for 12 hours. Right? So in a day, I'm going to only run the lights for 12 hours. So you take the 12 and multiply with that number. Right? You got a big number now. You got a big number now, right? Now how do I make that big number small? I don't want any more micromoles, but I want now express that as a moles of light. So what do I do if I have to express by moles? You divide that by 1 followed by 6 zeros. Right? So let's do that math. All of you do the math, and if you're not getting the same answer, raise your hand. Okay? The question is, I am giving plants 100 micromoles of light, 100 micromoles per meter square per second for 12 hours. Same intensity for 12 hours. Just that, in 1 day, 12 hours dark, 12 hours light period. So how much total light did plants receive in 1 day? And I want to give me that number in moles. Moles per meter square per day. Okay, it's a very simple math, right? Moles, not micromoles. Moles. Okay, what's your answer?
So 4.32.
4.3. She says 4.32 moles of light coming down per meter square area in what? Not 1 second, right? It's in 1 day. Moles per meter square per day. Did anybody get the same number? 4.32. 4.3 to 4.3. What about this group? Did you get that number? You have calculator. Turn it on your phones. You have calculator, right? Yeah, go ahead, do the math. Very simple math. 100 times, 100 is the number that I'm telling you, 100 micromoles, right? Times 60 seconds in a minute, times 60 minutes in an hour, times 12 hours in a day. That is a big number, right? Divide that number by 1 followed by 6 zeros to convert micromoles to moles. And then you should get 4.32 or something like that. Okay? We'll do the same math this afternoon, but in a little bit bigger way. But that is called DLI, daily light integral. Daily light integral. You see that equation there? That's exactly what you did. You take a number x micromoles and multiply, divide that by a million and then multiply 3,600 seconds per hour and start the number of hours per day of lighting. You get that. That's the same equation. In this case, 4.32. 4.32. The reason why this is important is plants don't respond to per second light intensities. Because every second the light changes. And if they are trying to adjust to every second, it's waste, resource waste for them. Plants count the number of photons they receive in a day and they try to respond to those daily integral values. Okay, that's more closely related. DLI is more closely related to plant growth. And that's why I want you to remember that. You see that right there, the picture there, those are lettuce plants. It's a leafy greens, like your spinach is lettuce. Okay? And on left side, we grow lettuce at 15 moles of light. 15 moles per meter square per day. On the right side, the same variety, same time started, but with only 10 moles. And you can see the response plants. You can see that the plants with 15 moles grew bigger, darker green in color. They're nice structure, whereas the ones in the other ones are less light. They are a little bit yellowish. They're smaller in size. They're also elongating. So that's how important the light intensity is. I did not talk anything about energy, right? I just said moles, number, all the time. Moles. I didn't even care about energy. I didn't talk about energy. Still, intensity is so important. But rather than giving in micromoles, the sensor gives you in micromoles, you should always convert that number to moles per meter square per day. It's the same concept as micromoles. It's just a bigger number expressed on a daily basis. It's an integral value. That's what it is. Okay? So remember so far concepts. Light intensity, irradiance. We talked about DLI now. Daily light integral. DLI. Acronym. Okay? It's 1 o'clock. I think I have maybe, 1, 2, 3, 4 slides. I may need about 15 minutes. What can we do? 15 minutes will finish up everything. So that's the lectures for today. And then we can talk about, okay, let's do that. Alright, so we talked about light intensity, energy. Okay. Now we're going to talk about light composition. Alright. Light composition is also called as light quality. You can also use the term light quality. Composition and quality are very same. Okay. So what does composition mean? Composition, remember that par, what is the wavelength for par?
400, 700.
400, 700, right? So when I get to composition, you know what I'm asking? I'm going to 400 nanometers. What is the intensity of 400? What is the intensity of 401? What is the intensity of 402? For every single wavelength, I want to know the intensity. That's what the graph is telling, isn't it? Look at that, 400 to 700 on the x-axis. Y-axis is intensity, but you can follow that line, and for each line, if you draw perpendiculars to the x-axis, you will know the intensity of each waveband, each wavelength. I can also use this graph and measure the intensity of blue, green, and red. You see the 3 bands there, blue, green, and red colors? 400 to 500, I can total all of the photons in 400 to 500. I can say that is blue intensity. Then I can total all the photons in the green band and say this is green intensity. And I can also say this is the red intensity. When I take the total light, photons, 100 micromoles, and split it into 3 or 4 dozens of wavelengths, then I'm calling it composition. That's quality. I'm now telling that, yes, there is 100 micromoles of light coming, but out of that 100 micromoles, 50 micromoles is red, 25 is green, and maybe 25 is blue. That is composition. Intensity just gives you the total number of photons, all of them together. But when you get to composition, you're splitting that into maybe 3 bands, maybe 5 bands, or maybe every wavelength if you want. We have sensors. A spectroradiometer is used to measure that intensity. That gives you a curve like that. And you can take that curve and you can point all the way to 444, way at the peak. Oh, that's like 0.75 micromoles. So we have 0.75 micromoles per meter square per second for 444 nanometers. For every wavelength you can get it, or you can combine them into wave bands like blue, green, and red, and tell how much blue light is coming, how much green light is coming, and how much red light is coming. When you split that intensity into individual wave bands, you're talking about light composition. Why is light composition important? This is one example. You see that picture down here on the right side? On the x-axis, you have wavelength. Again from 400 to, well, it's a little bit more than 400, but look for 400, 700 nanometers, blue, green, and red. On the y-axis is now photosynthesis efficiency. Okay? What do you see in that picture? Can somebody interpret that graph for me? Look at the graph. Which color of the light has more photosynthetic efficiency?
Red.
Yellowish red. Orange.
And then when you go to green, goes down, and the lowest is in what? Blue. So now it's not 100 micromoles of light. If that 100 micromoles of light has got 50 micromoles of blue, although I'm giving 100 micromoles, I'm giving 50 micromoles of stressful light to plants. That light doesn't increase photosynthesis based on this particular data, right? So photosynthetic efficiency is affected by light composition. Some wavebands are more efficient at photosynthesis than others. And I showed you the reason for why that happens on the picture on the right side. If you give plants red light, you see that electron in that electron transport path, it's getting excited, it's going up. But then if you give blue light on the right side, it is more excited than red light, but that there is excess energy there. But that excess energy is simply wasted out. That's why it's less efficient. Red has the right amount of energy needed for photosynthesis. That's why it is the most useful light in terms of vegetative growth. So it's not just the intensity that matters, it's also the composition. If somebody comes to you and say, hey, you have a greenhouse, we're almost done, 5 minutes. Hey, I'm giving you, you got to buy lights for your greenhouse, and I have a light that gives you 1000 micromoles. Good. But you should ask another question. What is that question?
Which light?
What is the composition of your light? And then he says, hey, I got a light that's got about 70% green light. Plants are green in color. Why don't you buy green light? Will you buy it? Not according to this graph. That's why composition is so important. But if I come to you and say, I got a light, it's got only 10% of the blue, maybe 10-15% green, and a lot of that is red light. Yes, and it may still give you 1000 micromoles, but still that is more useful because that favors growth. This is why composition is so important. Does it make sense to all of you? Why composition is important? I'm going to show you an actual example here from our own research. You look at this. Again, lettuce plants, a little bit busy picture, but picture is better than 1,000 words. Look at that. There are 4 different varieties of lettuce. Lettuce is like spinach or your amaranth or whatever. It's a leafy green, okay? 4 different varieties, and each variety is grown with 3 types of light. Now, warm white, purple, and cool white lights. There are 3 types of light, okay? Down below in the table, I'm showing you what is warm white, what is purple, and what is cool white in terms of composition. For example, take that warm white. What percentage of that warm white is blue? 20%. Do you see that? Go to cool white, it has got 25% blue light. But then now look at the green light. The warm white has got 44% green And the cool white has got 46%, lot of green. Almost half of the light is green light. But then the other one, the purple one, the middle one, look at that, it's got almost 70% red light. So there are three different lights. We measure their composition and we grow the same varieties, and you see the picture now. I want several of you interpret that picture. Now the first question is, do all plants look similar in that picture? No. No. Which light is the best light? Regardless of the variety, the middle one, the purple one, the plants are bigger. Why is purple bigger? Why the plants are bigger in purple? By the way, I forgot to tell, all these three lights of same intensity, 350 micromoles. The intensity was not different at all. We only played with composition. And then you're clearly saying that purple is the best. This is right before your example here. Okay? Now, look at the color. You have a bluish color, bluish red color. Where do you see more of that color? Which light gives you that color? Now in some varieties there is no color at all, but in some varieties there is a bluish red color, right? Which light gives you more of that color? Does purple give you more of that bluish color? Or some other ones? Take a look at the picture. Cool white. Cool white gave the smallest plants, but the color is dark purple. You know sunscreen? Why do we apply sunscreen? To protect from high intensity energy, right? Plants have a sunscreen. You know what it's called? Anthocyanins. Anthocyanins is a pigment plants produce to protect themselves from excess light. And what is the color of anthocyanins? Purplish blue. Now go back and tell me why that cool white is purplish blue in color. It's got more anthocyanins. Why do they have more anthocyanins?
Sir, it has
More of
blue,
blue and also more of green. Both of them have higher energy than red. So when you give plants with more energy, two things are happening. Their growth is going down, but some of the pigments are going down. Now anthocyanins for plants are like protection for protection. But for us it's a healthy compound. When we eat more anthocyanins, it's good for us. So here is a situation where kind of like a trade-off. I want big plants, but I also want healthy quality plants. When I sell it to my consumers, they are getting nutritionally high value plants, quality plants. So you can probably grow plants for almost 3 weeks with a lot of red light, purple light, and then just that last week, you may want to turn on your cool white light to just get the colors. You can do a little bit of tweaking, and that's only possible in greenhouses, not outside in the field, right? Just an example. But again, remember, this is the last slide, but again, remember, light intensity is one thing, but composition is also important. You need to know what is the color that is there in that light. I just showed an example. If you give lights same intensity but a lot of green, they don't do well. Okay? Remember that. And the last thing I want to talk about is photoperiodism, and you kind of explained that. Phytochrome, and I'm explaining in this slide, I'm telling you how phytochrome works. Photoperiodism, okay? This crop is poinsettia. This is just like your chrysanthemums, okay? But this is more of a holiday crop for us in the United States. Christmas time, we want to give gifts to people with the red, beautiful bracts, small pots. So we want them to flower right around that time, okay? But let's talk about chrysanthemums. If you grow poinsettias, if you grow poinsettias in long days, what do I mean when I say long day? What is the daylight?
So more than 12 hours.
Should be more than 12 hours. Remember that, more than 12 hours. If I grow them, that's how they look. Do they have any colored bracts? They are green colored leaves all the time. They will never turn red in color. But when I put dark cloth, like we talked, dark cloth, and reduce that photoperiod to 10 hours, then they start producing these beautiful red bracts. That's what we want to sell them, right? So how does this happen? How does this happen? How do plants know that it is dark and it's a short day or a long day? And like you said, it uses that pigment, phytochrome. So phytochrome exists in two forms. It can be a little bit complicated, but I'm going to try and explain it very simple way. Okay? It exists in two forms. Phytochrome red phytochrome far red. Two forms. Phytochrome red, phytochrome far red. Phytochrome red is called P subscript R. Phytochrome far red is called P subscript FR. Okay, two forms of phytochromes. PR, PFR. So in the morning, when the sunlight is falling, the PR form absorbs the light and becomes PFR. Okay? When the light is turned off, there is no light, then PFR turns to PR. So it is a conversion between these two forms. These two forms are dynamic, they change. One form can convert to another form. When there is sunlight, PR gets converted to PFR. And when there is no sunlight, when it's dark, the PFR now becomes PR. Okay? You understand so far, right? So let's say if I have a long night period, what happens to the total amount of PFR? Well, PFR changes to what? PR during night time. Now I'm saying the night is quite long. So all the PFR has converted to PR. So the PFR amount is less. Remember this, right? Because the night is long, right? You have created more dark time. All of the PFR has become PR. That's what plants use. The percentage of PFR to total phytochrome, if that is consistently less, plants now know that it's winter, short days, and less flower. That's how the PR and PFR phytochrome concept works in plants. It's the amount of the PFR that's the most important thing. Most active form of phytochrome is PFR, phytochrome far red. If that quantity is consistently less in plants, that is a signal that plants use to identify that it's winter and they should flower in short periods. Okay? That conversion. Okay? We'll stop here. I just want to review things that we talked about today. We talked about the radiance or energy, right? It comes from the wave nature of light. We talked about intensity. It comes from what nature? Particle nature of the light. That is, the term intensity is important. Okay? We are counting micromoles per meter square per second. From that number, we derived another integral number called what? DLI, daily light integral. Okay? And then afterwards, I showed you that it's just not the intensity. You may have the same intensity, but you got different colors. They may affect how plants grow. I've given you examples. The reason is photosynthetic efficiency. Red has the highest efficiency. Blue has the lowest. So you need to know how much light is there, intensity, but you also need to know the composition. Right? Quality. And then finally I talked about photoperiodism, which is another, it's not related to photosynthesis or growth, it is related to flowering. And I talked about phytochrome and phytochrome far red and how the total amount of phytochrome far red, consistent if it's less in plants, the plants then know that it's winter and they should flower. That's how it happens. Okay? Some very, very basics. Okay? Very, very basic. We're going very fast pace here. But this information should be sufficient. Next time you read a book, a textbook on light, this should figure out, I know what light intensity is, I know what DLI is, I know why composition is important. Okay? I will stop here. Sorry, it took a little longer than 15 minutes longer, but we had a little longer morning session, so I do want to complete. This afternoon we'll do a little bit math and fun stuff. I'm going to ask you to download some apps on your phone and we'll play with that. If there is a greenhouse, that'd be great. If not, at least they'll go outside and do something. Whatever was for us. Okay. I'll leave it to you, sir. Whatever you want to do.
Thank you, Professor. I will just speak to this for a couple of minutes.
Yeah, please take it.
In fact, we are in a process of checking your names so that there should be no spell mistake while preparing your certificates. Despite taking all care, there had been some spell mistakes. Like in the name of Dr. Manindra Mohan. It was Maninder Mohan written. It is Manindra. Because I know you personally, that's why I was very much cautious about the name of this gentleman. The same way, let me check it again. Miss Aditi Agrawal. ठीक है, तुम्हारा नाम मुझे पता है. अंचल करोल, मिस अंचल करोल. ठीक है, क्योंकि इसमें ये भी नहीं लिखा. डॉक्टर अंजू पाल. आप spell your name correctly. Miss Ursula Safi. This is Bhupesh Singh Koshiari, entrepreneur from Haldwani.